Okay, so 3.1, we're going to work on this example 4 and have you guys try 5 and 6. What we're going to do is apply some transformation rules. Okay, you maybe want to make note here. In your notes, 1.7, section 1.7 has our transformation rules. I hope you didn't throw away those notes packets. At least wait till after the semester exam to do something like that. Okay, so, horizontal shifts, vertical shifts. Sometimes things were stretched, compressed, and then we had reflections with negatives. Those are about the 6 different transformations we worked on. So they apply with exponential functions too. So if we're starting with a parent function of 2 to the x, when I add a number inside the function, that was always called a horizontal shift. And then there's a negative out front, which is a reflection. Okay, so here, go ahead and write this down. I'm going to walk you through number 4, and then I'll have you try 5 and 6. So whenever we add something inside the function, I know it looks a little different, but let me just go back to quadratic rules. Let's just say we had y equals x squared, and we had y equals x plus 1 squared. Well, if the plus 1 was here, or if the plus 1 was out here, there was a difference, right? Vertical, horizontal. Right now, this is considered inside the function. Okay, so we say horizontal shift 1 unit to the left. All right. And then with reflections, either the negative was inside or outside. Okay, once again, go to 1.7 if you need a little more review on that. But when the negative is outside the function, it's always a reflection over the x-axis. Inside would look like this. It'd be 2 raised to the negative x. If you saw that, now we call that kind of inside the function, we'd say over the y-axis. Okay. All right, and that's all they're really asking for, right? Describe the transformations of the graph of f that yields the graph of g. So what happened from there to there? Okay. All right, so you think through 5 and 6, and then we'll give you some feedback on that. All right, so here we see the negative. That's inside the function. Notice a different location. Just got to kind of commit that to memory. It's the reflection over the y-axis. And then now the number that's being added or subtracted is on the outside of the function, or outside the parentheses. So we call that the vertical shift, okay? So you kind of have an idea what that would look like compared to above, because we have 3 to the x up on number 2. Actually, we skipped that one yesterday, but I have it here. So I'd reflect this over the y-axis. So it'd be kind of looking like this. And then it's shifted down 4 units, okay? So end up kind of looking like that. All right, number 6. Well, we can compare 6 to number 3 up there. We do have that one graphed. So this one is going to go 2 shifts going on, right? So you subtract 5, it's going to go to the right 5 units. So something about a horizontal shift, 5 units to the right, and then it's a vertical shift up 3 units. So this exact graph right here is going to be picked up, moved to the right, and then shifted, what, up 3 units? So it had that same look, just translated. Okay. All right, so yesterday we recognized and evaluated exponential functions with base A, so base 2, base 3, base 1/2. Today we'll also get to base E. We graphed yesterday, and we started doing some transformations today. All right, next we're going to solve exponential equations, okay, and we're going to work towards the same base. There is another method we'll learn in the next semester, but we're going to work towards the same base today. And then we'll finish with a couple application problems, okay? All right, so example 7, where it says solve this equation for x. These are exponential. When the unknown is up here, it's different. They're not quadratic, they're not linear. We need different techniques for solving these. So here, write down this success criteria up above. Step 1, we want to work towards the same base. What does that mean? Like right now, I have a base of 2 and a base of 16. They're not the same base. So we're going to work towards the same base. Once we get the same base, we're going to move on to step 2. This is also called the one-to-one property. It says this. If you have the same base, so if a is raised to the u equals a raised to the v, then what we can do is set u equal to v, set the exponents equal to each other. Okay, If you want to add the name to it, go ahead. Below it, I'd call that the one-to-one property. The authors might say that in the directions, so that's why it might be important to write that down. Okay, and then you're going to solve the result. Whatever u equals v is, it's usually linear, but sometimes quadratic. We use our other algebra skills to just solve that equation. You can check the solution as well if you have time and want to add that fourth step. All right, so I'm going to show you 7 and 9, and then I'm going to have you guys try 8 and 10. Here we go. Step 1, work towards the same base. You usually want to work with the bigger number. I can't take 2 and write that with a base of 16, unless I get really fancy. It's a lot easier to take the bigger number and break it down. So you start playing with the powers. 2 squared is what? 2 to the third is what? And so on. 2 to the fourth is 16. So I replace 16 with something that's equal to involving the same base. Okay. All right, so now I'm on to step 2. I can apply the one-to-one property. I have the bases are the same, so now I'm going to set u equal to v. So that's kind of why I lightly circled this to show you. All right, we're going to take x plus 1 and set it equal to 4. And now solving the resulting equation is the last step. Okay, so we get 3. See, it's different. To start exponential equations, we don't use the quad formula. We don't factor. It's a different approach. Work towards the same base is one approach. Okay, let's take a look at 9. Now this one's a little bit different. When you have something written as a fraction, the first thing I recommend is get that number 3 to the numerator. Okay, and how we can do that is using this, I guess it was 8 in the negative n in your notes yesterday. So right now we have 1 over 3 to the first. So how can I write that with a base in the numerator? I've got to write as 3 to the negative 1. These are equal. If you want to add that off to the side, go ahead. Okay, so I'm going to replace 1 over 3 with 3 to the negative 1 so that I can get towards the same base. This one's tougher because we're actually going to change both sides. And this will take a little bit of practice to get used to. Okay, so this is 3 to the negative 1. And then 81, I can take that big number and break it down. Once again, just playing with the powers. All these won't be memorized. It's okay. Guess and check with your calculator. 3 to the fourth is 81. Okay, I'm almost there. I'm almost to step 2. My bases aren't quite the same. I just need to apply that other property we learned yesterday or reviewed. Power to a power, we multiply. So that is going to be 3 to the negative x. Okay, now I'm there. Now I can set my exponents equal to each other and solve it to get negative 4. Okay, your turn. Try 8 and 10. Should take maybe about 3 minutes, and then we'll go over it. All right, so this is the bigger number. We can get by with just changing one side. So 27 is replaced with 3 to the third, and we're ready. 2x equals 3. We get 1.5 or 3/2. 10. Now here's where you want to get that number upstairs. Okay, we don't want to take 6 and put it down in the denominator. That's going to be a little more complex and confusing. All right, so I first started, it's up to you. You could write 216 in the negative first power right now, or I changed the 216 to a base of 6, but eventually I got to bring this up. So that's 6 to the negative third. Okay, so like I said, the other option is to write 216 to the negative 1 right now, and then you got to change that to 6 to the third raised to the negative 1, which gives us negative 3. So another way to show the work to get there. Okay. All right, so now I have the same base. I set those equal, and we get negative 7. Okay, moving on to the natural base. E should have been introduced to this last year in Algebra 2. So real quick, quick introduction without going through some crazy theorem in the formula for E, but it's just used in a lot of applications. The most convenient choice for a base is this natural number E. It's not a variable. That's one thing you just got to remember right away. Just like the variable pi in your calculator, it's stored. So let's make sure we know how to find e to the x. It's right here. See that blue e to the x? So if I hit seconds, e to the x, it's going to ask me to punch in an exponent. So I'll just put e to the first. And there you go. There's the 2.718 number that they're talking about in the notes. Okay, so just know it's a number that is programmed in your calculator like pi. Okay, just has different meaning than pi. So construct a table of values for this function. Sketch the graph of the function. Okay, so like we did yesterday, if my input value is -2, we're going to do e to the -2nd, which is 1 over e squared, but really this is an irrational number. We can't express as a fraction anyways. We're just going to need the calculator. So whether you do e to the -2nd or 1 over e to the 2nd, doesn't matter. Okay, so I end up with 0.135. So approximately 0.14 is the nearest 100. All right, now if you want to quickly get this table going though, feel free to use your y equals. So if I do y equals e to the x, like that, okay, I can get these values real quick, right? Since we're just using decimal form, go to my table, second graph, and I could pull from these pretty quickly. There's the -2 that we already wrote down. What's -1? 0.37. Okay, so I'm just going to continue to copy these down. This is 1. This is 2.718 because we're raising it to the first power. And then when we square it, we're around 7.39. Plot the points. We should see a graph a lot like we saw yesterday showing, yesterday we did 2 to the x. This is just 2.718 to the x. So it's going to have that same look. So -2, very small. -1, small again. Y-intercept, okay, don't forget your asymptote at y equals 0 so that you draw this correctly. Your line needs to be right along the x-axis, and then it increases quickly. Hence the phrase exponential growth. All right, what I want you to do for this one is I want to edit something to this. I want to put a -3. I want you to see a horizontal or vertical shift on this one. So keep all that the same and then add to that -3. Okay? All right, we'll use the table of values again, but what I want you to realize that when we multiply by 2 and 0.15, that's going to change the shape, but this is a vertical shift. So since we know we have a horizontal asymptote at y equals 0 for the parent function, if I pick that up and move it down 3 units, my horizontal asymptote will shift 2. So everybody right now, I want you to go ahead and write in your new horizontal asymptote. Okay, creates a little fence for this graph. So I'm even going to label it HA at y equals -3. That shifts down with the graph. Okay, from here I'm going to punch in the calculator and then show you the table. So try that as well. All right, there we go. We'll throw that in there. Our table should produce these values. We're plotting them. Nearest tenth will be fine. When you estimate these, whatever you chose is fine. Just round with accuracy with whatever you choose. Okay, so we're at -2. We're at -1.5. Here's the points that I had. And then you can just kind of keep going right along that asymptote. That's all we drew it there. Okay. Give you a moment to catch up on that. Okay, this next set of problems. Now they just have a base of e, but those steps we worked on solving exponential equations can be the same. We're going to use the one-to-one property. Base e, so we can set u equal to v and solve it. So we're going to subtract 1, divide by 2 to get the answer. Same thing with 14, but it's quadratic. Okay, so I'm going to pause here now and let you try to solve this one and solve that one. Set everything equal to 0 and then see if you can factor it to get the solutions. Okay.